Good evening, everybody. My name is Asad Mirza, PhD candidate, BME department. And on behalf of the MBS, I'm going to be doing the last MATLAB workshop seminar that we had planned, which is on MATLAB data presentation. So without further ado, let us begin. So first off, why bother trying to prepare how you do your data? Well, this picture pretty much highlights it. By default, if you're trying to communicate your data, what your research is, you want it to be easily understandable to somebody who doesn't really know your field. So if you just show them this plot on the left, that just has data on the X, the Y, no units, multiple different curves on your graph, all the same color. You have error bars here, but they don't have any context to them. It's just very messy and not a good way to show your data. However, on the right, which I found online that was made in MATLAB, you can see like, oh, you can see that the x-axis is length, y-axis is mass, but then you also have this confidence interval, which explains the error bars and how it diverges. And then you have a little legend explaining what each little part of the graph means. All of these make for a more readable and understandable graph. And this is essentially the goal of trying to communicate your data to whatever your audience is. To go from here to here requires not that much extra knowledge of MATLAB programming, but you'll see that there are a couple tips and tricks that you can use to go from here to there more easily. So let's just get started. So first you have to understand, how does MATLAB organize figures? So the way it works is you have this sort of all-encompassing thing called a figure, and within a figure you have what are called axes. Each graph that you make is its own axis, and each axis can have lines and text. So, and then each figure can have a legend. So if this whole thing is a figure, it has a single axis for this plot, then it has looks like 7 lines, no text, and then it has a legend that's on top of this figure showing each of the lines that are within the axis. And if you want to make this graph, you just do plot magic 5 and then legend. Very straightforward. Now, let's first talk about figures. So figures hold axes and color maps, and if you want to grab the property of the figure, you can use the command GCF for get current figure. And when you grab the current figure in MATLAB, you can now have it as an actual variable in your workspace. And then you can change pretty much anything about this figure. So as an example, if you were to do g.color, color is one of the properties of this get figure function. And you can now make it B for blue. And then now you can go from the regular default to a blue color. Axes hold plots. So you can use GCA rather than GCF to get the current axis. And now that you have this, every single aspect of the plot itself is held under ax. And for example, if you just type in ax.children, let's say, that'll tell you everything that the current axis is plotting. So you can see here, oh, ax.children is returning a 5x1 line array, showing you each of the different lines from this axis, which would be from the magic 5 that we plotted earlier. And similarly, you can do like x.color and make it black for k, and then now the background is black. So bare bones, that's how you access each. If you want to change something about the figure, you use GCF. If you want to change something about the axis, you can use GCA. So now the best way I can explain the power of this is just give you guys a demo and work through it. So what this demo is going to be, we're going to plot sine, cosine, and tangent. And by default, if you try to plot it in MATLAB, it looks like this on the left. So we're going to try to go from here, which would be like our bare bones, not very understandable graph, to what it looks like on the right, which is far more readable and understandable. So let's go ahead and do that. So I already wrote the code, and I'll be sharing this with you guys afterwards, so you can check the video description. So first, clear CLC, close all. So first, let's actually create these sine, cosine, tangent functions. I'm going to use linspace to go from negative 2 pi to 2 pi with 100 points in between, and just use sine of theta, cosine theta, tan of theta. And now let's just straightforward plot theta versus sine, theta versus cosine, and theta versus tangent. And then I'm going to do xlim to restrict myself between the x values of negative 3 pi over 2 and 3 pi over 2, and the y from negative 3 to 3. And for the tangent plot, because it has this vertical asymptote, I'm going to actually make this have a dash dash representation. So when you plot it, it looks like this. Not the best, but we're getting there. So keeping this right here, let me go back to MATLAB. And actually, let me see if I can dock this on the right here. There we go. And another way you could have done the plotting is by using the symbolic toolbox if you have that toolbox installed. And in this way, you can just use fplot sine of x, fplot cosine, fplot tangent of x. And if you do this, you don't have to mess around with these vector stuff. But for now, I'll just keep it as is. Now, we're going to edit each one of these plots. And how are we going to edit each? Well, if you look back up here, when I made the plotting command, I actually saved it to a variable, plot sine, plot cosine, plot tangent. And if you take a look at your workspace, you actually have plot cosine, plot sine, plot tangent, and there are line variables. So if I take a look at plot sine, for example, it opens up a property inspector. And these are all the properties that you can actually change for this line function. So what I'm going to do is programmatically do some changes. So first I'm going to make the line width of all of them 5. So if I just run this little put right here, now all the line widths are 5. Now I'm going to add a legend to this graph because we need to know which one's sine, cosine, tangent. But I'm going to save it to a variable. And when I've saved it to a variable, now I have data 1, 2, 3, but now I have a variable here. And I can edit this variable in a similar way. So I can do hLegend.location and say best outside. So now the legend goes outside. And then I can change what the string is by doing h.string and then just typing in a string for each one of my graphs. And now you can see here we have sine of theta, cosine theta, tangent theta. The graph is starting to get closer to a nicer, more presentable thing. So now let's go ahead and grab the axis in the figure. And let's say we want to make the background of the figure white for now. And now the background's white. And let's start editing this axis to get things looking better. So first thing I'm going to do is I'm going to change the aspect ratio. If you notice here, it's longer on the Y than it is on the X. So if I change the aspect ratio, now it's a nice square. So it's more visually appealing. Now there's a sort of box on the edge here that's sort of encompassing the entire figure. So I'm going to go ahead and turn this off, put this x-dot box off. The font, I'm going to change the Times New Roman. I'm going to make it bold and a size of 20. And these are changes that happen there. Now, if you notice here, the x-axis sort of starts off on the lower left-hand corner here, meaning like all the numbers sort of are bounded by this point right here. So what I'm going to do is I'm going to change the x-axis and y-axis location to start from the center of the screen instead, which is usually how you'll see the sine, cosine, tangent plots being made. And if I do that, now everything starts off from the center. Now, let's add, so instead of putting -4, -2, 0, -2, 4, I'm going to actually rotate the x-axis ticks 45 degrees. So you can do tick label rotation. I'm going to say the tick values are now actually going from -pi, pi/2 to pi. So now I have this numerical representation. But instead of putting -pi, pi/2, I actually want to put the symbols for it. So you can do x-axis tick labels instead of values and replace each of these values with their character arrays instead. And now I have -pi, -pi/2, pi/2, and pi. I'm going to add in the minor ticks on the x and y. And the last thing I'm going to do is, if you notice here, the graph is sort of obscuring what the actual x-axis and y-axis are saying. So I'm going to do x.layer top, which puts the numbers on top of everything. And one last thing I'm going to do is, if you notice, the tick labels are all going towards the right or towards the top. So I'm just going to do axe tickter both. And now they're both going to left and right. So now it's a bit better to look at. And now if I bring this out, this is far more presentable than what we had before, which was this on left. So that is the little demo I wanted to show you guys. And before I continue, any questions?
Yeah, the tick there is tick direction, correct?
Yeah.
Okay.
And if you ever want to know what other properties you can change, you can usually just go axis. Or actually go GCA. And this will show you a little documentation of it, and you can see access properties here on the bottom. And everything on this list is something you can change of your graph. Similarly, if you type in GCF, this will tell you how to use GCF. But more importantly, if you go down here to figure properties, this is everything you can change about your figure. So it's good to know that these two exist. So now that we have that, how do you actually go about exporting these figures? So if you actually want to share it with somebody, how do you do that? So here are my suggestions. Avoid taking a picture with your phone. That's not exactly the best way to do it. Although I have seen students do that, and it's just not good. No, don't do it. Avoid using the snip feature if you have Windows, because while it does work, it's not exactly that professional, and you get a lower quality snip, really. And MATLAB has this option where you can copy a figure. If you go down to the edit menu and do copy figure, and that also works, but it has a tendency to also go for a low resolution than you might want in your figures. So I would avoid using that as well. So what should you use? MATLAB has a dedicated export tool for just this thing. So using this export tool, you can change the figure size, background color, font size, some of the options that we were changing manually. But more importantly, you can save these export settings to a settings file and then use them over and over again. So if you have, for example, a setting for a specific resolution and size of a figure that you want to maintain, you can save that as a style and then keep using that for later figures. So then you can change things, for example, the height and width of your figure, both in inches, centimeters, and points, so pixels on the screen. You can change the font size, so you can change the size, name, wave, angle, and the widths and the line styles as well. And then one more important thing to note is you can actually change the color space that you're going to be exporting with. So, for example, you can pick an RGB, which is the standard. You can use a black and white or a grayscale if that's how you want to export your data, if you're going to be using it for maybe a print that you don't want to be doing color printing for. Or if you're going to be sending it off to a print shop, note that printers actually use a CMYK color space instead of the standard RGB. And if you're wondering what the difference is, it's mostly visual, so hopefully you can see this on the right here. This is two different figures that you could be printing. And on the left, they're under the RGB color space, and here's how they look like. But under the CMYK, here's what they look like. It's a bit more dulled, but this is the color space that's used by printers. So if you send out something on the left for printing, what you'll actually get is something more on the right. Now, they might look very similar to you, but there is a subtle difference in color, and if you don't account for this difference, you'll get an incorrect print. And the last thing you really need to decide when you do exporting your figures is do you want to export it as a vector or a bitmap? Now, here's the difference. Vectors are pretty much a mathematical representations of your figure that are invariant of scale or skewness. So it doesn't actually matter how much you zoom in or out of a vector image. The detail stays 100% crisp and perfect because you're not actually zooming in on any pixels or anything. You're zooming in on something that is defined by a mathematical relationship. So even if you zoom in 100 times, all that happens is the figure updates itself using a mathematical equation to however resolution it should show to be crisp. So, but if you zoom out 100 times, it'll still use that same mathematical representation to show you a perfect image. However, if you instead export as a bitmap with pixels, you're limited by how many pixels you use to recreate the image. So you can see here that if you use a coarse amount of pixels, then you can make out the image and it'll likely be smaller in size, but if you zoom in, you can actually see the edges of the pixels. Another thing to note that MATLAB will give you control over is something called DPI, which stands for dots per inch. Quite literally, how many dots do you have in your image per inch of it? So the standard is 72 dots per inch, but you can make this as however high you want. So for example, 300 dots per inch, 600, 800, 1,000, whatever. And a lot of journal publications actually request that when you submit your figures, you give it at a specific length, width, or height or whatever, and a specific DPI. So for example, I know in a paper I recently submitted that they requested all the figures be at 600 DPI. So I had to go in MATLAB and actually export my figures to be 600 DPI to adhere to their standards. So how do you actually export these figures? Well, you can use the actual exporting feature in MATLAB, like I showed you, or you could use a command instead. As everything in MATLAB, there's usually a code thing behind everything. So in this case, the command is print the file name that you want, dash the format type, and dash the resolution. So for example, you can do print and then just a file name. So you can say like chart1, for example. The format type, so you can do like, for example, dash dtiff if you want a TIFF image. And then you can do dash resolution. So you can do dash R0, in which case it will use your standard screen resolution, dash 300 for 300 dpi, or dash R600 for 600 dpi. So if you do print chart1 dash dtiff dash R300, that will give you a file called chart1 that has a format of a TIFF file that is 300 dpi in resolution. Simple enough. You can also change things for a bitmap versus a vector. So if you want to use a bitmap, you can use these file types. If you want to use a vector, you can use a PDF, you can use meta, EPSC, or an SVG. So let me go ahead and show you guys this. So if you go here to export, setup, here's everything I was talking about. And you can change the rendering space as needed. You can also change your resolution here. So you can say like 150, 300, 600, or auto screen as well. Or you can just type in a number here, like 1,000, let's say. And then you can change what your font size is, custom fonts, anything in your computer will show up in here. And then naturally the lines as well. And then you click apply to figure and it'll apply it. Now I already have a custom setting for high resolution. And if I load this, the thing about the high resolution is I automatically set it to Times New Roman. I always set my font weight to bold. I usually use a 600 dpi. I usually keep the background to white. And I usually export as a vector instead of a bitmap. So I have infinite resolution essentially. And then you can click export. And then it'll say, okay, how do you want to export? And you can say, oh, I want to use, I don't know, let's say a PDF, and I'll say test one. Oh, PDF. Where is it? There it is. Test one, let's say. And if I save this, close this out, I have this test one thing here. And if I open it outside of MATLAB, you can see I have my image I made here. Naturally, because I didn't set any specific settings, it's sort of scaled already. You can see here, it doesn't matter how much I zoom in, it's perfect quality because I was using vectors. However, if I had instead, let me grab all this and run it. If I had instead done export, high resolution, load, and now I did OpenGL instead, and I clicked export, and then I said, let's say test two, And let's say this was a JPEG instead, and I saved it. I can see I have a test2 image here. And if I open this up, you can see here, even though I have 600 dpi, you can see some aliasing located here because these are pixels. So it's not a perfect image, but usually if you're trying to share something on the web, maybe this is enough for you. But if you want to share something that is going to be scaled, either very small or very large, you might want to stick to vectors instead. So that's a major difference. And let me just quickly delete these two and show you how you can use the export results. So you can do, for example, change the renderer to OpenGL. Oh, I actually closed the figure, so let me just run it again. Here's my figure. I can change the renderer now to OpenGL, and if it's OpenGL, that's for bitmaps. So I can save it in the same format as a TIFF file with a resolution 600, or a BMP, or a JPEG, or a PNG. And if I run these, MATLAB will start creating these files and drop them into your current folder. So there's the BMP, there's the JPEG, there's the PNG, and there's a TIFF. And if you open any one of these, you'll be able to see them. And because they're all bitmaps, they all have that issue of the actual being constrained by how many pixels they have. Some are worse than others. I think JPEG is the worst because it actually is a image standard meant for compression. So when you actually save something as a JPEG, the file size is going to be small, but the resolution is going to be rather poor. So for example, if I open up here and we take a look, if you notice here, JPEG is 307 kilobytes, while a BMP is almost 26 megabytes. TIFF is about 2 megabytes, PNG is about 168. So these are different compression artifacts that are going on. So a BMP generally has a very nice resolution. Even if you zoom in a lot, it'll still look fairly nice. On the other hand, if you try to look at a PNG, you'll start seeing aliasing happening. And in JPEG, like I said, is probably the worst with regards to this. On the other hand, if you switch over to painters for a vector image, and then you do the print, I have all these vector images being made. So let's take a look at the figure here. So this is on a PDF and a vector. So because it's a vector, no pixels at all, perfectly crisp line that you can scale or scale smaller or larger, and it'll never change in its resolution. And I think I can show another example. Open with, hopefully this will open. Maybe not. So here's the EPS, but it doesn't seem to show properly. So here's the SVG. So similar to the PDF, perfect resolution. You do not see any pixels because it's a vector. And that was that. So before I start talking about different types of plots, any questions?
Yeah, overall, when you say there's a vector versus a bitmap, it allocates more memory space in order to represent the mathematical models.
It sort of depends. So if we take a look and compare the file sizes, so you can see here a vector image is only like 7 kilobytes. And even if you look at the SVG, it's about 7. So like the biggest thing here is the bitmap. And pretty much all the bitmap images are large, but the vectors, because they're just mathematical equations, are relatively smaller in comparison. It's just that usually when you're trying to share things online or host images online, they use bitmaps, which are easier to read and understand than these vector images, which are just mathematical equations. So it's a sort of trade-off. Yeah.
Thanks.
All right. So next thing I want to show you guys is some other types of plots that you can do in MATLAB. So for example, you can do error bars, which is useful for showing standard deviations in data. You can use a scatter histogram, which is useful for categorized data that have distributions that you want to compare against. And if you want to plot different functions, you can use f implicit or f implicit 3 for plotting functions that have multiple variables. And this is particularly useful if what you're trying to solve isn't actually a function. So if you try to do the vertical line test, if you guys remember that, it passes through multiple points, meaning it's impossible to isolate a single variable y equals f of x, because for a particular y value, you get multiple x values, or for a particular x value, you get multiple y values. So you're going to need an implicit function. So let me go ahead and show this for you guys. So error bars, if you have X and Y data and you have the standard deviation or error of them, you can just do this. And if we apply what we just learned, let me dock this, we can change the font weight. And then here are all similar things that we just did, where we grab the axis, and using the properties, I can change what the labels are, the font name, font weight, the line width, and so on and so forth. And now you can get something on the right here. So you need data points, values, and so forth. Next thing would be a log. So if I run this instead, you can see here, I'm trying to plot this in the log space at this exponential x times sine of x. And then I do similar types of changing to the x and y axis. And you get this type of graph here. And then here's one on how to use scatter histogram. So if you load this patient data set, for example, and let me actually do a clear here and load patients. This is a little data set that has like age, whether or not that patient is has a what exactly their diastolic pressure is in millimeters mercury, what their gender is, their height, their last name, their location, their health status. So if they're excellent, good, poor, whatever, if they're a smoker or not, what their systolic pressure is, and what their weight is. And if you want to plot and compare these against each other, you can actually just create a table that says the last name, what their diastolic systolic pressure is, and if they're a smoker or not. So if I make a table of this, you can see here you have their last name, their diastolic systolic pressures, and if they're a smoker or not. And if you do scatter histogram, you can see here, you can see the relationship between their systolic and diastolic pressures. And everything that's blue means that they are a smoker. Everything that is sort of orangish means that they're not a smoker. So you can see here, if you're a smoker, you tend to have a higher systolic and diastolic pressures. And if you're not a smoker, you tend to have lower systolic diastolic pressures. And similarly, we can do some changes to the graph. And now this looks more presentable to something for a publication. Now here's how you can do the f implicit. So let's say you're trying to plot this at y times sine of x, x times cosine of y, tangent x times y. If you try to normally try to isolate y, you'll find that it's an impossible task. There's no possible way you can isolate y by itself. So you have to use an implicit function to plot this. And here's how it would look like. Similarly, you can go to 3 dimensions, and if you try to isolate, figure out what z is, for example, you'll find that it's an impossible task to do. So instead, what you can do is f implicit 3, and then do the same plot for this. And now you have your plot. So I just wanted to go over that. So those are some simpler line plots. And before I continue on to volume visualization, any questions?
Yeah, the implicit function will only be for graphs that are implicit, right?
Yeah, as the name would suggest. If you have a function that you can't represent as y equals something, that would be an implicit function.
Thanks.
Yeah. So now for volume visualization, you can show how, for example, stream particles are changing over time. If you know what the velocity and position are for your particles, you can do, for example, stream tubes, which is useful for showing volume in space. You can also show slices of 3D data, which is useful if you're dealing with like CT or MRI data or echo data even. So let me go ahead and show this. Close this. So you can load in this wind data, and you have the UVW, which is the velocity in the X, Y, and Z dimensions, and the positions in the X, Y, and Z dimensions. And you can see here it's a three-dimensional matrix. So X, Y, and Z. So the velocity in each of these points. So the X velocity at each of these points. Same with the Y, X, Y, and Z velocities and their position values. And if I do a stream slice, and then I try to interpret the stream speed, and then I plot it, let's see if we can grab this. So this basically just figured out what the vectors are for everything. And now that I have this information, I can go ahead and do this stream particles, pass it to iVerts, tell it to animate it for 50, for I believe this is 50 frames, I forget. And now if I run this all at once, it plots the velocity streamline at our particular value for Z, which I believe is 5 in this case. And then it just shows you what's going on. So that's an example of stream particles. Stream tubes is similar. So if I load in wind, so if I do a clear, and I load in wind, again, you have the UVW, X, Y, and Z. And if I make a mesh grid this time, a mesh grid will give me a way to sample in the X, Y, and Z space. And then if I do a stream tube with a shading interpret, I can actually now see, oh, I got a little vortice here. I see the X, Y, and Z there. And I can rotate this as I need. So that's one way you can see three-dimensional data. And this last one is if I want to see slices of 3D data. So if I have this function here, this hyperbolic tangent times x times exponential of this, and I want to just see a slice at, let's say, x equals 0.8, then I can just use slice, give it the x, y, and z data of my mesh grid, give it the v data, which has all the values, and say I want to just see what the value is at the x slice. Ignore what the y is. I want to see all the y, but I want to focus in on the z equals 0 slice. If I run this instead, then I get this. So you can see here, we're at the z equals 0, and we're at the x, so this is the x-axis. We're at the x of 0.8, and for the y, it's showing all the y's. So rather than just showing a single cross-section value here, it's showing all the values for y. That's why we get this intersection. And with that, I think I'm done. Any questions?